So hello, my name is Alexandra Heater, and like Shai said, I work for PMP Optica, a hyperspectral imaging company with solutions tailored for the meat industry. I'm going to be talking about how we're using NIR spectroscopy for hyperspectral imaging detection of myopathies as well as foreign material. Just briefly what I'm going to go over, I'm going to go a little bit into the background of spectroscopy and spectral imaging. I'll talk about how we're transferring this technology into industry, which is a rather difficult ask sometimes, as well as some of the current applications, so woody breast detection, foreign material detection, and then just some final thoughts. Jumping right in, spectroscopy is the branch of science concerned with investigation and measurement of spectra produced when materials interact with or emit electromagnetic radiation, aka light. Examining how light interacts with materials reveals several processes influenced by their chemical composition and physical attributes. So these include absorption, scattering, transmission, and reflection. Absorption occurs because the energy of the incident photons matches the energy gaps between electronic states in the material. The absorbed photons excite electrons to higher energy levels, causing electronic transitions or molecular vibrations. Light can scatter in different directions due to interactions with the microscopic structures or particles within the material, or it may even pass through the material without any absorption or scattering. The extent of transmission depends on the factors such as the material's transparency, its thickness, and the incident wavelength that you're looking at. Finally, some of the light may be reflected back from the surface of the material. The amount of reflection is dependent on the surface conditions of the material, such as its roughness or the difference in refractive index between the material and the medium surrounding it. And of course, the overall intensity will be reduced because of the other interactions from the processes I just mentioned. Each of these processes contribute to the overall behavior when light interacts with the material. Specific outcomes depend on the wavelength of light, chemical composition, structure of the material, and of course, surface conditions. The technology used in the applications I'm talking about specifically utilizes near-infrared or NIR spectroscopy, a method that captures and processes information in the NIR region of the electromagnetic spectrum, which is typically between 780 and 2500 nanometers, which is just beyond the visible spectrum perceivable by humans. Our technology focuses on wavelengths between 900 and 1700 nanometers. The fundamental principle behind NIR spectroscopy lies in the interaction of the NIR light with specific molecules, altering their vibrational modes. This interaction results in characteristic absorption, reflection, and scattering patterns, influenced by molecular bonds, functional groups, and molecular arrangements within the sample. Changes in the vibration of the molecules give rise to overtone and combination bands, predominantly involving carbon, hydrogen, oxygen, and nitrogen, which is great for us because that's what most organic materials are made of. Overtones in spectroscopy refer to higher energy vibrational modes of a molecule that are multiples, so typically twice or higher of the fundamental vibrational frequency. In case you didn't know, everything does vibrate. For example, if a molecule vibrates at a certain fundamental frequency due to a particular bond, such as oxygen and hydrogen, the first overtone would correspond to vibrations that are twice the frequency of the fundamental mode. Combination bands arise when two or more vibrational modes interact simultaneously to create new vibrational frequencies. These bands can provide additional information about chemical composition of the structure being analyzed. The molecule diagrams on the slide, so the really pretty circle diagrams, demonstrate the major vibrational modes in the NIR region. Our NIR spectrometer detects the changes in reflected light caused by these changes in vibrations, which provide information about chemical composition and structure of the sample being analyzed. Since the molecular structure of most compounds is rather complex, the resulting spectra are actually the result of many overlapping peaks and valleys. Most chemical and biological products exhibit a unique absorption and reflection that can be used for both qualitative and quantitative analysis. So spectroscopy is great, but let's talk about hyperspectral imaging, which I'm going to actually use that term. Maybe because that's what we claim to do, which is what we do. While NIR spectroscopy focuses on analyzing specific wavelengths for chemical identification, spectral imaging expands this capability by capturing comprehensive spectral information across a wide range of wavelengths for each pixel in an image. This approach enables simultaneous examination of chemical composition and spatial information, with the data organized into a spectral cube. NIR spectral imaging is great for analysis of complex materials since it can measure multiple elements without affecting the technique's capabilities or the material being measured. Essentially, it's a non-destructive measurement, which is important when you're trying to measure things that are going to be going out to consumers. Depending on the number of wavelengths being analyzed, the spectral imaging technique may be classified as either multi or hyperspectral. Multispectral imaging analyzes data at a limited number of discrete wavelengths or bands across the electromagnetic spectrum. Typically, multispectral imaging involves 10 to several dozen bands. Hyperspectral imaging analyzes at many more narrow and consecutive bands across the spectrum. So this can range from 10 to hundreds or even thousands of spectral bands, providing a more detailed and continuous profile of the sample. Both techniques can differentiate unknown chemistry, but they do so in slightly different ways because of their difference in spectral resolutions. Multispectral can differentiate between materials that have distinct spectral signatures with limited number of bands it captures. So for example, if a material you are analyzing has good absorption or reflection properties in the specific wavelengths in the multispectral imaging space that you're looking at, you will be able to differentiate it. But if not, there will be no information for that type of imaging technique to actually isolate those materials. Hyperspectral imaging offers a much finer spectral resolution compared to multispectral imaging. This allows for more precise identification and differentiation of the material based on their unique spectral signatures across a broader range of wavelengths. So while both techniques can differentiate unknown chemistry, hyperspectral imaging is generally more effective for tasks requiring precise identification of materials based on subtle spectral differences. To illustrate my point, here is a multispectral image of a couple of the more common form materials found in processing facilities with NIR light. I'll just give you a minute to kind of take it in. Now this is the same materials in hyperspectral imaging. Clearly there's less gaps in the data. The absence of gaps ensures comprehensive information without missing important spectral transitions. This detailed spectral information often leads to higher classification accuracy compared to multispectral imaging, particularly in complex scenarios with overlapping classes or where the distinguishing features are primarily spectral. However, it should be noted that hyperspectral imaging requires training and optimization for effectiveness. It also presents challenges such as increased data volume, higher computational requirements, and the need for specialized algorithms for data processing and analysis. Despite these challenges, the advantages of hyperspectral imaging often outweigh the drawbacks in scenarios where detailed spectral information is critical for achieving accurate and reliable results in machine learning applications. Now that's the actual science behind it, but one of the primary challenges associated with this type of technology is its practical application into real-world scenarios. Spectroscopy in general is rather sensitive to its environment in which it operates in. Successfully transferring this technology into industry hinges on addressing several critical factors. So these include environmental conditions such as temperature, humidity, illumination, having to handle caustic cleaning chemicals, running at production speed, the inherent variation in product that you'll see on the daily to the monthly to the yearly. And then also, on top of all of that, having machine learning capabilities that can process information in the matter of seconds. So kind of my shameless plug, on this slide is an image of our machinery that we've developed that is successfully performing NIR hyperspectral imaging in both primary and ready-to-eat plants. It has been designed to operate at speeds up to 120 feet per minute and handle up to 60,000 pounds an hour depending on the application. The operating temperatures range from 32 to 50 degrees Fahrenheit with a maximum relative humidity of 90%. It is IP69K or equivalent compliant, and it seals on all of the enclosures that we use. It's not hermetically sealed, but there is no direct exchange between environmental air and enclosure air. We have a cabinet dryer to make sure that any change in air between the two systems is dry, and as well as a chiller to maintain internal temperatures for machine production. On the software side of things, this machine generates over 20 terabytes of data a day and makes 16 million decisions per minute. Handling this volume of information in real time requires hyperspectral image processing, which includes normalization, correction, dimensionality reduction, and data processing. To interpret this data in real time, we have advanced AI algorithms that are continually processing, analyzing, and communicating information to the other parts of the machine. As a part of the correction process, the system compensates for instrumental artifacts, environmental changes, and baseline changes, thus improving the precision and sensitivity of the spectral analysis. Successful deployment of this machine also requires robust data collection. It's essential for machine learning models to have sufficiently large data sets that include expected product variation, which may require a few weeks of passive data collection at any given site that this machine is being implemented at. Now, the part that you actually care about, turning to the applications. Let's first examine fillets affected by woody breast myopathy. Woody breast is a myopathy observed in broiler pectoralis major, characterized by its tough, rubbery texture. This condition affects modern, rapidly growing broilers with high breast yield, leading to decreased meat quality due to undesirable changes in the muscle texture, which may result in meat needing to be downgraded or discarded, impacting profitability. A Canadian study in 2022 analyzed that 70.5% of the fillets that they were looking at should be considered severe woody breast, 11.8% modest, and only 17.7% normal. While woody breast is safe to consume, its altered texture, color, and potential changes in nutritional composition may not align with what consumers prefer or their dietary expectations. Currently, detecting woody breast relies heavily on manual methods, such as palpating breast to assess hardness. The severity of woody breast is graded based on these tactile assessments. Giving way for human error, it's time-consuming, can result in uninspected chickens going out to the consumer, and even increases the risk of foreign material with all of the additional manual manipulation. While previous studies have characterized woody breast based on pH, color, texture, and changes after cooking, there is currently no standardized method for objectively measuring woody breast. Vision systems can be used for this kind of detection. They rely on detecting visible changes in the appearance of the meat, such as color or texture anomalies. Woody breast can vary widely in color and texture, leading to high rates of false positives, which is identifying non-defective meat as defective, or false negatives, missing defective meat. This variability makes it difficult for vision systems to reliably differentiate between normal and woody breast. Another type of system that you can use is X-ray, which is effective for detecting internal defects and foreign material in meat depending on their density. However, woody breast meat poses a challenge for X-ray systems because of the density differences between normal and affected meat are relatively subtle, making it difficult for X-ray systems to consistently distinguish between them with high accuracy. NIR light, on the other hand, can penetrate into biological tissues to varying depths depending on the tissue type and composition. For chicken breast tissue, NIR light typically penetrates on the order of 0.5 to 5 millimeters. Given the chemical changes to the breast tissue and the possible penetration depth, there is potential for NIR hyperspectral imaging to effectively detect and analyze these changes. With that in mind, we conducted a study at a partner production facility to develop a machine learning model using NIR that would divert woody breast from a production stream. Since there are qualitative levels to woody breast severity, the following definitions were used for data collection and classification model development. Grade 0 is breast that has no hard areas and is very flimsy. We called that no woody breast at all. Grade 1 is a ridge forming where the breast meat intersects with the chicken tender. We also called this mild woody breast for our operators who were doing the analysis. Grade 2, the meat has a rubbery texture on the skin side lobe area. You can start to feel the striations in the muscle, and the ridge between the breast meat and chicken tender is more defined and very hard. There may be some spaghetti breast seen, but this is not a direct correlation with woody breast, and we considered that moderate woody breast. Finally, grade 3. The meat is hard throughout. You can visibly see the hardness. When placed on the edge of a bin, the meat stays generally taut and doesn't slope. Color changes can be pretty severe, changing from a soft pink to a yellow white. And again, you may see spaghetti breast, which isn't directly correlated, but will be seen with woody breast. This was also called severe woody breast. The main objective of the model was to sort out severe woody breast, or grade 3s, from the production line with the least amount of other grades sorted out. we developed a modified system of what I showed you originally in the technology transfer section. This system was designed to run at 100 feet per minute with 2 production lanes to accommodate in-factory throughput. All samples were scanned 3 times in each lane in different orientations, and there were 2 independent graders from our partner facility independently assessing the woody breast. So the following are the steps that we took to actually do this methodology. To collect enough samples for each of the grades, at the beginning of each day, the chicken breasts were run at production speed through the system. The system then sorted chicken breasts into separate bins for grade 1, 2, or 3 if it detected it. This was done using a base model that had previously been developed for woody breast detection from earlier data collection. Once the bin 3 was filled, all bins were mixed together randomly, and a portion of the grade 0s that passed by were then also put into that bin. Grade 0 has the largest population because they were generally smaller in size compared to the other grades, and thus more would fit in a single bin. The randomized bin was then handed over to the manual graders, who independently graded each chicken breast before the data was captured by the system. We did this additional step of running the production through our machine to begin with to improve the time needed to acquire grade 3 woody breasts, and also to allow for a comparison of the initial model bias to that of the independent graders. In addition to reviewing the differences in grade frequency between the base model and the graders, the individual graders are also compared with each other to evaluate the bias between 2 people, or in this case we had, I think, about 4 people given the same grade criteria. There was evidence when looking at the results that grades contain human error. On average, there was a difference of 5% of the time the graders being off by at least 1 grade, and there were situations where certain graders were different up to 20% of the time. Once data was collected, the chicken breasts were then post-processed to ensure only the meat sections were included in the training and testing of the model. The spectral signatures of each grade were then provided to the machine learning for model development. So the results. The model does a grade prediction first by averaging the spectral data over the entire chicken breast, and then the final decision is made once that's been averaged and the machine has looked at it. The table on the right, known as a confusion matrix, displays the results of the model classification. The matrix displays the number of correct predictions, so true positives and true negatives, and incorrect predictions, so false positives and false negatives, made by the model. Final model results showed this study was successful, with predictions of grade 3 woody breast detection rate of 80.51% and a false positive rate, when broken down, of 0.26% of the grade 0s as grade 3s. 2.82% of the grade 1s is grade 3s, and 28.99% of the grade 2s is grade 3s. Now, looking at these results, I know that the grade 2s have a rather high false positive rate. When we were looking back at this data, we came to some conclusions around the fact that this data set had been defined qualitatively based on a visual and manual inspection of the chicken. This is not as scientifically accurate because it's already inherently got human bias in it. What we decided from these results, and specifically if you look at the grade 2s, you can see that on the matrix, most of them are actually getting classified as a grade 1 or a grade 3. Clearly, scientifically, the grade 2s are not in the middle. There's some that are just beginning to have woody breasts and some that are much more severe. That makes sense because people are going to be trying to evaluate a chemical change in the system by just touching it. That's not really accurate scientifically. One of the considerations for a future application of this type of technology would be developing a data set that's got a more scientific basis on the actual initial data being provided for model development. But this type of technology clearly is able to distinguish between healthy and unhealthy woody breast. And then the other thing to consider is how this would actually apply into industry. This type of technology would be removing chicken breasts from a facility's production line, which would in turn cause lost profits. There are other options for having this as a rework, so that would be something that you would have to consider, or partnering with other industries that are looking for breasts that are typically lower in water concentration for other applications such as pet food. The other application of this technology that we're a little bit more knowledgeable in is foreign material. And when I say foreign material, I specifically mean in-plant manufacturing materials that you're going to see on the production line. These include pulp products such as wood and cardboard, plastic, so hard and soft plastic, so LDPE polypropylene acetyl. Engineering materials such as rubber, like O-rings, personal protective equipment, cotton, and bone. Now, the reason we care about this is more of an insurance policy. If any of these materials go to a consumer, it can result in a recall, which is hundreds of $millions and not a good look for any customer out there. While humans are one of the main ways of doing detection, they're not very reliable. We tend to get tired when we're looking at the same thing for 8 to 12 hours a day. There have been studies that have been previously done on that. I'm not going to touch too much on it, which is why most manufacturing facilities look into using other technologies. I'm going to go into them just because this is what currently are the standards for in practice. X-ray. X-ray penetrates through materials and food packaging, and they can interact differently with materials based on their density. For materials such as metal, glass, stones, and certain plastics, they typically have higher densities compared to food products. This density contrast allows X-ray imaging systems to distinguish between foreign materials and the surrounding food or packaging that they're looking at. Unlike other inspection technologies, X-ray can do internal inspection. This is kind of one of the biggest advantages of this technique because neither VIS or hyperspectral or any other human interaction can find foreign materials embedded inside the materials. Where there's limitations in this technology is the low density materials which do appear in manufacturing facilities. So that includes your liners, sometimes cotton, cardboard, those kinds of materials this system will not be able to detect. Lower density plastics have a lower atomic number and density, allowing X-rays to pass through them more easily, but it can result in lower contrast and reduced visibility for the X-ray to distinguish. Camera systems, specifically visual systems, are a surface technology effective for inspecting food products and packaging. They can detect foreign materials that are visible to the naked eye or those that cause visible anomalies in the appearance of the products. This includes contaminants like insects, hair, fibers, or large pieces of foreign material that may be present. They also are low cost generally and the most accessible and easy to implement of the technologies. This makes visual imaging accessible to a broader range of food manufacturers, particularly smaller scale operations. They're really good at high contrast materials, but their limitations are faced when the materials start to look closer to the product they're being analyzed. And then we have hyperspectral imaging, which instead of looking at contrast of materials or density, it looks at the chemical signatures. This means that you get a lot more information. So RGB is three values. Hyperspectral can be thousands of wavelengths that you're actually analyzing for differences in these materials, which means that it's very good at a broader range of foreign materials compared to the other two imaging techniques that I just talked about. Some of the limitations, it's rather expensive because of the type of technology that it is, and there are limitations surrounding spectra when materials look similar to each other. Going a little bit more in depth into that, highly reflective materials. So very shiny materials will reflect all light that is incident on them. This means that a droplet of water, a mirror, or a shiny piece of metal can have very similar spectral or reflective properties. This would not be able to be distinguished by a machine because they look spectrally the same. And kind of on the opposite end, but the same idea, very dark materials. So materials that are very dark will absorb all light, so no information is reflected back to the detectors. Not all black items absorb every wavelength in the NIR, meaning that they can be detected, but in the event that it does, it will be virtually indistinguishable from shadows, which means that that type of foreign material will not be able to be detected. We did an in-plant comparison at one of our other partner production facilities comparing these three types of technologies. This was done using size foreign materials on product that was scanned through each of the systems. If it was detected at a reasonable detection size, it's given a check mark. So that's what this table is representing. If you look, the results make sense for what I just said about the types of technology. X-ray was able to find metals in the high density plastics as well as bone. Vision system was able to detect the high contrast materials, so the blue, and hyperspectral imaging had the broadest range of what it could detect. Now you'll notice there are three materials that weren't tested with hyperspectral imaging. That's because at the time of this study, we actually incorporated a vision system with ours because we already knew the capabilities of those materials with high contrast materials. It kind of lends itself to the practice in industry to use a multi-hurdle approach. No one system is going to be able to find everything. Using a multitude of different detection lets you get the broadest range and the highest resolution for these foreign materials. So just some final thoughts. Hyperspectral imaging does have applications in the poultry industry. And not only the poultry industry, foreign material detection can be done on multiple different types of products, a large range of materials. You can do quality analysis such as woody breast myopathy, and there's future applications, just to name a couple. We're currently looking into disease detection on offal as well as fat lean analysis. Any questions?